Welcome to our intermediate course in logic. Intermediate because it falls between the first course in logic and the mathematical logic sequence that is offered at the 400 level. We introduced this course because people were having trouble adjusting to the big difference between the baby logic course. I think it's Philosophy 100, but it's a standard intro course to logic, and the mathematical logic course at the 400 level, which does meta theory. So the purpose of this course is to go beyond the first order logic system, introduce some meta theory. We'll also do some modal logic in the second part of the course, and we'll do some non-monotonic logic in the third part of the course, focusing on Bayesian probability theory, Bayesian confirmation theory. The textbook for the course, the primary textbook for the first part of the course, is the Ted Sider book. This is all information that's on your syllabus. There's also a supplementary book by David Papineau. Sometimes it helps to hear the same material in a different voice. So it's worth looking at the Papineau book, though it's not a required textbook for the course. For the third part of the course, you won't have to buy anything. The part of the book that we're going to use is available online. In addition to that, the kind of proof theory that I'm going to introduce you to is a Lemon-style proof theory, and there is an online proof checker through Texas A&M University called the Logic Demon, and that's available online as well. The only thing that's a little bit dated about it is that you have to use ASCII characters only. So some of the logic symbols, you're going to have to see what they use in place of the usual logic symbols, because the logic symbols are not ASCII characters for the most part. For example, the quantifiers are not. Since this is a second course in logic, here's some things that would be useful for you to already have become familiar with. For the first logic course, the course focuses on the proof theory and the semantic apparatus for standard first-order logic. So a language was introduced, proof rules were introduced, and then you talked about, when it was propositional logic, you talked about truth tables as the semantic apparatus for first-order logic. And when quantifiers were introduced, you used some basic model theory. So you had domains and you had extensions for each of the predicate letters, which were subsets of the domain, that sort of thing. If that sounds familiar to you, or vaguely familiar for what you remember from your first logic course, that's good. Some of you will not have had a first logic course, but have a strong background in math. A strong background in math, from my perspective, means something after calculus, because the crucial thing is that you have been introduced to the idea of a mathematical system and thought a little bit about what goes into a mathematical system. If you have that kind of a background in math, this course would be fine. You don't have to have taken a first course in logic. It is helpful, though, to take a look and figure out as much as you can about what a first-order logic system looks like. So one of the first things we're going to do here is learn something about the variety of first-order logic systems. In all likelihood, the sort of proof theory that you were introduced to in your first-order logic course is called a Fitch-style proof system. Fitch-style proof systems involve assumptions that are indented, or you use an arrow pointing to a little subproof. You bracket off the subproof, and then you can't use those lines anymore after you get outside of the assumption that you made for purposes of the subproof. That's called a Fitch-style system. We're not going to do that. The alternative is a Lemon-style system. That's the one that I want to introduce you to, and we're going to use that for purposes of this course. Both of these kinds of systems are called natural deduction systems. That's because they focus on inferences, inference patterns that we find in ordinary reasoning. An alternative to a natural deduction system is an axiomatic system, where you try to limit the number of primitives that you have for your system. The result is a mathematically elegant theory, but it turns out to be cumbersome to do proofs inside of an axiomatic system. The proofs get very long, complicated, and not clearly intuitive in helping you to see why the conclusion follows from the premises that were given to you. The Cider book uses such an axiomatic system, so we're just going to bypass that. When the Cider book asks you to do a proof in an axiomatic system, we're just going to say, do the proof, but don't use the axiomatic system. Just use the natural deduction system that we learned. So what's distinctive about a Lemon-style natural deduction system? The answer is, in place of the subproofs and the indentations that you got with Fitch-style proofs, what we do is introduce a further column. The column that we introduce is called the assumption set column. Natural deduction systems all have numbered steps for the proof, and each numbered step, each line of the proof, has a formula on it. Either the premise or one of the premises that you were given, or something that you derived from the premises that you were given. So you have the content of the line, you have the line number, and then you have a justification column where you cite the rules that allow you to write down the formula that you wrote down. In the justification column, you not only cite the rule, but you cite the previous line numbers that the rule appealed to that allow you to apply the rule. So all natural deduction systems have line numbers, contents of the line, the formula that's involved in your proof, and a justification column. And you're done with the proof when you get to the conclusion of the argument that you were given as a problem. What's distinctive about Lemon-style systems is that we add an assumption set to each row in the proof. So for each row, you'll have an assumption set, a line number, a formula, and a justification for that formula. The assumption set tracks which of the assumptions are being used to generate the line that you have. We'll look at some examples of how that works later on, but here's an advantage of this system. In Fitch-style systems, when you get inside of a subproof, you actually have invalid steps that are being done. You have steps that simply you can't stop at. You have to keep going. With Lemon-style systems, there's never a point at which you don't have a valid stopping point. Every line gives you a new argument. It tells you, here's a formula, it can be derived from these assumptions. And that's always going to be a valid step in the proof. Remember the notion of validity, by the way, from your first logic course. For an argument to be valid is for the conclusion to follow necessarily from the premises, to be derivable from the premises. So it'll be impossible for the premises to be true and the conclusion false. The other crucial notion here is soundness. I hope you remember that from your first logic course as well. A sound argument is one that is valid and also has true premises. We will primarily focus on the notion of validity here, though. The question of truth and falsity is typically outside the domain of logic. So suppose we decide we're going to invent a proof theory for a language. To construct a logic, we first construct a language, give the proof rules for deriving some formulas in the language from other formulas in the language, and then construct a semantics for that language. This makes the formal language of first-order logic much simpler than natural languages. Natural languages function off of both syntax, the grammar for the language, semantics, the stuff about meaning, but also some catch-all thing that is labeled pragmatics, where what's communicated using the language is a function of some part of the context that's not just semantic or syntactic. When we study formal languages, we get to abstract from the pragmatic element, which is useful because it's messy. So all we have to do is do the syntax and the semantics. The syntax we'll talk about first. The syntax begins by telling us what are the particles, the linguistic particles that go into the language. So we introduce, say, sentence letters. We can also introduce names or constants and predicate letters. We use parentheses and that sort of thing. And we culminate this first step of the logic by giving a definition of a well-formed formula. It turns out to be a recursive definition. So for propositional logic, we say, we've got sentence letters, P, Q, R, S, and so on. If you want, you can introduce subscripts on them as well. You then say that each of these atomic formulas is a well-formed formula. That's the base clause for our definition. We then also introduce connectives. Connectives or operators, it doesn't matter. But negation is the weird one because it's called a connective, even though it simply operates on a sentence of some other sort all by itself. So if P is a well-formed formula, then so is tilde P. Typically, though, what we use is negation. We have a symbol for negation, a symbol for disjunction, typically expressed in English using the word or. We have a symbol for conjunction, typically expressed using and, although there are lots of different ways of expressing conjunctions in English. We have a symbol for conditionals, for implication, and we have a symbol for biconditionals, arrows running both directions. For our system, we'll begin this way. We're going to use a V as our symbol for disjunction. So P, V, Q says either P is true or Q is true. We're going to use an ampersand for conjunction. For implication, at least for the first part of this course, we're just going to use a simple arrow. A single arrow is our symbol for implication. So P arrow Q says, if P, then Q. And we'll use a double arrow for biconditionals. P, arrow going both directions, Q. That completes our list of primitive vocabulary for the language, and our definition of a well-formed formula started with the base clause that I gave you. All of the atomic formulas, the ones that have no connectives in them at all, count as well-formed formulas, and then we introduce a special recursive clause for each of the connectives. So if P is a well-formed formula, then tilde P is a well-formed formula. And if both P and Q are themselves well-formed formulas, then P wedge Q is a well-formed formula, P ampersand Q is well-formed, P arrow Q is well-formed, and P double arrow Q is well-formed. This is called a recursive definition because the P's and Q's in the recursive clause can stand both for the atomic formulas and for anything that turns out to pass scrutiny as a well-formed formula by the recursive clause, by the inductive clause itself. So once you get P or Q to pass scrutiny as a well-formed formula by one of the subclauses of the inductive clause, then tilde parentheses P wedge Q also turns out to be a well-formed formula. Then we close our definition by saying, as the third clause, nothing else counts as a well-formed formula except what gets counted in virtue of clauses 1 and 2. That completes our language. That's all we needed to do. We introduce the primitive symbols for the system. We give a definition of a well-formed formula, which turns out to be something like a grammatical sentence in the language in question, something that actually says something. Just a string of symbols counts as a formula. It doesn't matter what it is. But it doesn't count as a well-formed formula, a formula that is the analog of a grammatical sentence in natural language, except in virtue of meeting the definition of a well-formed formula that I just gave you. Once we have our definition of a well-formed formula in front of us, we are then in a position to introduce some proof rules. We introduce proof rules to show how to derive one formula that we don't yet have from other formulas that we do have. How do we do that? For each connective that we use, for each logical particle that we introduce into the logic, we want both an intro and an elim rule. We want to be able to introduce the connective in some way or other when we don't have it, and we want to be able to get rid of the connective when we do have it. So take ampersand. Ampersand you can get rid of in one step. So if you have P and Q, you now have an ampersand formula. To get rid of it, you can write P down on the next line, or you can write Q down on the next line. Either one will be perfectly fine. So we're going to get a complete system of the sort we're looking for just by using intro and elim rules for each of the connectives. So you should think, well, we'll have an intro and elim rule for negation, for disjunction, for conjunction, for conditionals, and for biconditionals. That would be correct. For most of these rules, we're just going to annotate them by citing the connective and putting a capital I or a capital E after it. So wedge introduction will be VI. Wedge elimination will be V capital E. If you look at this chart, you'll see how we're going to name them. Some rules, though, have such familiar forms and go by other names that we're going to use that instead. One of those would be arrow elimination, but we are going to use arrow capital E as our annotation. It's typically called modus ponens. So if you put down MP or modus ponens or something like that, you certainly aren't going to lose credit for using the more common name for the rule. We're going to use arrow capital E just because I want you to see the pattern that's going on here. For the tildes, however, we're going to use RAA, which stands for reductio ad absurdum. That's the most common name for the rule in question. The way it works, you're comfortable with this from your first logic course. You assume the opposite of what is claimed to follow, and you generate a contradiction from the denial of what follows. And that allows you to conclude that what you were trying to prove actually does follow, because contradictions can't be true. When we turn to the predicate logic part of first order logic, we'll have more terms, more symbols that we'll have to deal with. So we'll have universal and existential quantifiers, and we will introduce an identity, a special identity symbol. And again, we'll label those the same way. We're going to have universal introduction, universal elimination, existential introduction, existential elimination, identity introduction, and identity elimination. All of those will be the basic rules for the system. Each of these primitive rules not only has a name, but a form. When we get to the form for each rule, we try to be as permissive as we can. So in some logic systems, you have very restrictive forms. Think about ampersand elimination. You have P and Q. We're going to allow there to be two forms for that rule. One form says you have as a premise P and Q, so you get to write down P at the next line or some succeeding line. Another form of the rule says you've got P and Q on a line, so you get to write down Q. So notice you can do ampersand elimination to get either the first conjunct by itself or the second conjunct by itself. Other proof theories are restrictive and require you to only get the first conjunct. In order to get the second conjunct by itself, you'd have to appeal to commutation. Commutation is the property where you can flip the formula around. So you can go from P and Q to Q and P, and if one of them is true, the other one has to be true, and vice versa. Those are logically equivalent formulas. I don't want our proof theory to be tedious in the way that such systems make proofs be. So we're just going to introduce two primitive forms for the conjunction rule. For ampersand elimination, you can simplify to either the first or the second. Doesn't matter. We're going to do the same thing when it comes to disjunctions. Disjunctive elimination is an argument that looks like this. Either P or Q is true, and one of the two is false. That's your second premise for applying wedge elimination. So you've got P or Q on a line, and then your next line is either, or some other line, is either not P. That would be one form of the rule. Another form of the rule is where the next line or succeeding line somewhere is not Q. So if you've got P or Q on a line and you've got not P on a line, you can then conclude Q by wedge elimination. Similarly, if you've got P or Q on a line and you've got not Q on some other line, you can conclude that P is true. For ampersand introduction, there's also two ways of introducing an ampersand if you don't have one. Same thing for a wedge. What does it take to derive a formula P ampersand Q? Well, you've got to have P on a line, and separately you've got to have Q on a line. Now, when you put them together with an ampersand between them, it doesn't matter in this system which order you put them in. So if you've got P on a line and Q on a line, you can put P ampersand Q on a line. Or alternatively, you can put Q ampersand P. It doesn't matter which order you put them in. That's ampersand introduction. Wedge introduction allows you to go from P to the disjunction, P or Q. This is a mysterious rule in some people's minds, but think of it like this. P says something stronger than P or Q. If I say today is Thursday, then it follows that today is either Thursday or Friday, because the second disjunctive claim is a weakening of the first one. It's easier for the second claim to be true than it is for the first claim to be true. That's wedge introduction. From P, you can get P or Q, P wedge Q. But you can also get Q wedge P. It doesn't matter which order you put the two disjuncts. Arrow elimination is just modus ponens, which I described already. You've got that P implies Q, and you're told on a separate line that the antecedent P is true. The antecedent of a conditional is the formula that comes before the arrow. The consequent of a conditional is the formula after the arrow. So what you're doing is writing down the consequent of the conditional when you have both the conditional and its antecedent on separate lines. You can call that modus ponens if you want. I'm going to call it arrow elimination. Hold off on arrow introduction because that's an assumption rule, as are the RAA rules. The other primitive connective is the biconditional, the double arrow. And it too has two forms for each of the rules. So if you want a double arrow formula, to derive it, you have to have the single arrow running in both directions. So if you're trying to derive P double arrow Q, you need P arrow Q on a line, and somewhere on a different line, you have to have Q arrow P. Again, it doesn't matter which of these two formulas you put on either side of the double arrow. So if you've got P arrow Q on a line and Q arrow P on a line, you can write down P double arrow Q, or you can write down Q double arrow P. It doesn't matter at all. That's the double arrow introduction rule. Double arrow elimination allows you to get a single arrow from a double arrow formula. So suppose you've got as a premise P double arrow Q. There are two things that you can derive from this by the double arrow elimination rule. You can either get P arrow Q, write that down on a line and justify it by double arrow elimination, or you can get Q arrow P, justified in the same way. So for the wedges, the ampersands, and the double arrows, there are two forms for every intro and a limb rule. And these two forms are designed explicitly to keep proofs from being unnecessarily long. We complicate the primitive rules in order to simplify the proof structure once you get going on doing a proof. What we haven't covered are the assumption rules. So sometimes when you're doing a proof, you don't need to make any additional assumptions at all. That's great. It's a wonderful feeling when you look at it and say, using the first 7 rules that we just described, I can see how to get to the conclusion from the premises that I'm given. Other times, though, you get stuck. You can't see how to get to the conclusion. Now you're going to need to make an assumption. For propositional logic, there are 2 different kinds of rules, technically 3 different kinds of rules that allow us to make assumptions. There's RAA. Technically there are 2 forms of that. And there's arrow introduction. I've already described RAA a bit. So suppose you're trying to prove P. You don't see how to get it? Here's a way to proceed. Assume not P. If P really follows from the information that you were given, then the assumption of not P will be inconsistent with the assumptions that you were given. So you should be able to derive a contradiction when you combine not P with those assumptions. Once you get the contradiction, you can use the RAA rule to justify putting P down on the next line. So if you assume not P, and that generates a contradiction, you can then derive P from that little subproof that you just had. Similarly, suppose you're trying to prove not P. Suppose you have to prove not P. Either you're given that as a problem or the problem requires you to get to not P in order to complete it. Assume P. Derive a contradiction. That little subproof will then entitle you to put down not P. The last rule for the system of propositional logic is arrow introduction. It, too, is an assumption rule. So suppose you're trying to prove P arrow Q and you don't see how to get there. Here's how arrow introduction works. It says, well, assume the antecedent, P. Now try to derive Q from it. Once you do that, then your little subproof, no matter how long it is, can be summarized as follows. If P is true, then Q is true, because Q follows from the assumption of P. That's what arrow introduction allows you to write down on the next line. You assume P, you derive Q. So you summarize on the next line with P arrow Q, citing the rule arrow introduction. That's the 10 primitive rules for propositional logic. When we turn to predicate logic, the other part of standard first-order logic, the only additional things that we introduce some names called constants. Those are usually lowercase letters at the beginning of the alphabet, A, B, C, that sort of thing. We introduce predicate letters, P, Q, R, S, and so on, capitalized. And that gives us atomic formulas of the form P, capital P, lowercase a, which says A has P, or A is P. That's now a complete sentence, a complete thought, so will count as a well-formed formula. So primitive terminology for predicate logic allows P from propositional logic to be replaced and supplemented by capital P lowercase a, capital P lowercase b, capital R lowercase c. All of these things are going to count as atomic formulas in predicate logic. In addition, we're going to introduce variables for constants. So if you've got a lowercase a, b, c, d, etc., counting as constants in the language, each of those can be replaced by a variable. Variables will be lowercase letters near the end of the alphabet, X, Y, Z, and so on. So we now have predicate letters, constants, and variables And variables, once we have them in place, can either be free or bound. They are free when there's no quantifiers in the picture. We introduce quantifiers so we can have sentences like this. Everything has a property P. That turns out to be formalized this way. Upside down A, lowercase x, capital P, lowercase x. X is now a bound variable. It is bound by the quantifier at the front because that quantifier binds the x variable in the formula capital P, lowercase x. So capital P, lowercase x is a formula of the language, and it has a free variable x in it. If we want that variable to be bound, we put a universal or an existential quantifier on the front of it. Universal quantifiers are upside down A's. Existential quantifiers are backwards E's. Given all of this additional apparatus, we need intro and elim rules for universal quantifiers and for existential quantifiers. And they work just as you might expect. So if you have a formula that has no bound variables in it, so take FA, capital F, lowercase a, or capital F, lowercase x. Doesn't make any difference. Universal introduction lets you derive for all x, fx, from either of those two formulas. And similarly for the existential quantifier, if you've got capital F, lowercase a, you can derive there is an x that's f. You can derive ex fx, where the first e is a backwards e, the existential quantifier. Notice in each of these cases, you had a premise that didn't have either quantifier in it, and you derived something that now has a quantifier in it. That's why they're called universal introduction and existential introduction. Elimination rules work similarly. If you've got a formula with a universal quantifier on the front of it, you simply drop the universal quantifier and replace the variable with a constant. So if you've got for all x, fx, you can derive fa from that. Similarly, if you've got ex, fx, the existential elimination rule will allow you in some way or another to replace that with fa. I will describe quickly the identity rules that we'll use because we are at some point going to introduce identity into our formal system. This turns out to be an important additional element in the system. I'll describe why later on, but for right now, identity introduction just allows you to insert A equals A at any point you want in a proof and just cite identity introduction. A equals A is a theorem of standard first-order predicate logic. So identity introduction just encodes that as a primitive rule. Identity elimination allows you to take any formula you want. If you've got A is F, so capital F, lowercase a, and you also have as a separate premise that A is identical with, say, C or B or something else. Let's make it C for present purposes. So if you have as premises capital F, lowercase a, and A equals C, you can derive capital F, lowercase c. C is F. This is a substitutivity principle, the substitutivity of identicals. It turns out that will become a tendentious rule when we turn to modal logic, but right now in standard first-order logic, it doesn't raise any particular issues. Go back, though, to the quantifiers. We had quantifier rules for existential and universal quantifiers, and two of these rules look bad. It's important to realize this. So the ones that look good are, first, universal elimination. If everything has a certain feature, F, then you have that feature. The table has the feature. So universal elimination, where you replace a variable with a constant, that always works. At least in this logic system. We're going to see some systems that question whether or not that's true. But this one, it works for. Similarly, existential introduction has no concerns about it at all. So if you have blue eyes, then something has blue eyes. That's how existential introduction works, and there's no problem with that rule. The rules that are, well, let's just say, the rules that are clearly invalid are universal introduction and existential elimination. So with universal introduction, we want to go from A is F to everything is F. And in general, that's just a really boneheaded inference. It's a terrible idea to draw that kind of conclusion. So what we're going to do is introduce restrictions on when you can use this rule. We're going to introduce restrictions that are strong enough so that we rule out the cases that are boneheaded, stupid ones. In other words, we're going to try to introduce restrictions that are strong enough to make sure we don't have any invalid inferences. The way we're going to do that is to introduce restrictions on the constant that's in the premise. So remember, our premise was A is F. We're going to insist that A be arbitrary. So intuitively, the idea is it doesn't matter what constant you have here. It makes no difference at all. Then we can use universal introduction. That's the intuitive idea of the restrictions on universal introduction, that the name that you're generalizing on is really an arbitrary name. We'll look at the details of what those restrictions are in a moment. Similarly, for existential elimination, suppose you know that something in the universe has blue eyes. You have to be careful which individual you pick, though, to instantiate that general truth. So we have to do something similar here as we did with universal introduction. We have to introduce restrictions on which name you can introduce. And what we want to do is introduce those restrictions in such a way that the inferences that we draw would still go through had we picked a different name. In other words, we want something like arbitrariness here as well for the constant that we choose in the proof. So the important thing to remember is when we introduce the quantifiers, we make our system, our proof system, more complicated because we're adding new rules, but we also make it more complicated because we're now going to use some rules that are not universally valid. They have to satisfy certain restrictions before we use them. That completes our general discussion of the nature of a lemon-style proof system. I want now to show you what proofs look like when they're done properly as lemon-style proofs. So here's an example. Notice what we have in the example. As I said earlier, there are 4 columns here rather than 3 columns that you might be more familiar with if you learned Fitch-style proof systems. In a Fitch-style proof system, you'll have the line number column, you'll have the line, which is the formula at each of the line numbers, and you'll have a justification column. What's new here with lemon-style systems is that you also have an assumption set. The assumption set turns out to be important because in order to have a proof, here's what you're required to do. You're required to get to the conclusion that you were told to derive from the premises, and you can't rely on any assumptions beyond the assumptions that you were given. In this example, there are 4 premises. We're assuming that you were given 4 premises, which are lines 1, 2, 3, and 4, and that you were told to derive S from these 4 premises. That's what we do at line 10. So to tell whether or not we actually have a proof of the problem we were given, we look at line 10. We got to S, that's the conclusion of the problem we were given, and then we look at the assumption set. The assumption set includes lines 1, 2, 3, and 4. As I described the problem, we now have a proof because the problem that we're assuming we were given gave us those 4 claims as premises. and told us to derive S from them. So the way you tell whether you did that is you look, did you get to S, and did you rely on anything outside of lines 1 through 4? And the answer is no, you didn't. Notice, however, that we had another assumption in this problem. Line 5 has us assuming not S. Notice as well that when I annotated that line as an assumption, I put in parentheses what I was doing. That's not required for the proof. It's just a reminder to me, I made this assumption so that I could use the RAA rule. You can do that or not as it turns out to be helpful or not to you. It doesn't matter. So it's not part of the proof. It's just a reminder to me not to forget what I was doing when I made an assumption. So I'm given lines 1 through 4, and I'm supposed to get S out of it. But let's suppose I look at lines 1 through 4, and I can't really see how to get S using rules that don't involve making assumptions. I do see S. I do see S in line 2, but I don't see anything that would let me get the S part away from the R and P part in the other premises. So what I'm going to do is just assume not S at line 5. That lets me do something with line 2 using the wedge elimination rule. So notice how I annotate the justification at line 6. I cite the 2 lines that I'm going to use, I cite the rule that I'm going to use, and I write down as the content of line 6 the formula that follows by applying that rule to those 2 lines. What follows is that if S is false, then R and P has to be true, given line 2. So that's what I write down. Then I do ampersand elimination at the next line. From line 6, the annotation again follows the rule form that we're allowed to use, one of the 2. And then I do arrow elimination using line 1 and P from line 7. So 7 and 1 by arrow elimination, or modus ponens, if you prefer to call it that, gives me Q. If I have Q, then I can use line 8 with line 3 to do wedge elimination, giving me T. And that's what I was hoping to do. When I made the assumption of not S at line 5, I was hoping to get a contradiction. I knew I had to get a contradiction. I didn't know which contradiction I was going to get, where it was going to appear, but I finally got one. So line 4 tells us that T is false. Line 9 tells us that T is true. And so I use those 2 lines, lines 9 and 4, the T and the not T. I use RAA as the rule that justifies discharging an assumption. So assumption rules are ones where you make an assumption and you are told what you need to do to discharge that assumption by applying that rule. You make an assumption, then the discharge rules, RAA or arrow introduction, allow you to discharge the assumption and remove it from the assumption set. So notice what happened to our assumption set throughout this proof. The premises that we were given, 1 through 4, are all justified as assumptions. And every assumption has as its assumption set the very line in question. So when we get to line 5, that's not an assumption that we were given in the problem. That's an assumption that we made, but it gets justified in the same way. It's an assumption, and its assumption set is line 5. Notice then that after that point, every time we use a rule, we conjoin all of the assumptions for the lines that were used for the assumption set of the new line. So notice at line 6, we use lines 2 and 5 by wedge elimination. What that means is the assumption set for line 6 is going to include all of the assumptions for lines 2 and 5. Since 2 and 5 were just both assumptions, that just gives 2 and 5 as the assumption set for line 6. Notice carefully what the first column is. It is the assumption set. So first, it's a set. Second, it's a set of assumptions. Under no circumstances can you have a line number in the assumption set that isn't itself the line number of an assumption. It's only assumptions that show up in the assumption set. I emphasize this because I promise that one of the simple mistakes that you're going to make is annotating the assumption set incorrectly by putting a line number in there that isn't really an assumption. So for example, look at line 8. You used 7 and 1. We used 7 and 1 by arrow elimination to get Q. And one of the simple mistakes that keeps getting made is because you use 7 and 1, people want to put 7 and 1 in the assumption set. But that's a mistake because 7 is not an assumption. What you do is you put the assumptions for line 7 in the assumption set for line 8. So at line 8, if you use 7 and 1, you're going to have to carry down the assumptions for lines 7 and 1. 1 is an assumption, 7 is not. So 1 carries down from line 1, and 2 and 5 carry down from line 7. Similarly, for line 9, you use 8 and 3. Well, 3 is an assumption, but 8 is not an assumption. So 3 carries down, but so does the entire assumption set for line 8. Notice then that the assumption set line is cumulative to this point. Every time we use a line that relies on an assumption, that assumption gets carried down to the line that we derived. We add together the assumption sets for the lines that we use to get the assumption set for the line that we derived. The only time you subtract from the assumption set is when you use a discharge rule. For propositional logic, that's either one of the two forms of RAA or arrow introduction. In those cases, we annotate by putting the discharged assumption in parentheses after the rule that we cite. In the case of this problem, we used RAA, so we put 5 in parentheses after citing the rule. The rule then has to have some premises that justify the use of the rule and a discharge assumption noted as well. What we do when we have a discharge assumption is we look at the lines that are used at that step in the proof. We put all of them together as before, but this time we get to subtract the assumption being discharged. So at step 10, we used both lines 9 and 4. So we put together all of that. That gives us 1, 2, 3, 4, 5. But then we are discharging line 5 by RAA, so we get to drop that assumption from the assumption set. So what we're left with is 1, 2, 3, and 4. That's very nice because notice what we get as a result. We get the conclusion that we were supposed to prove, and we did it by relying on no assumptions other than those that were given in the problem. That was an example of what we do when we're doing propositional proofs in our lemon style system. What if we're doing predicate proofs? Remember, predicate proofs are going to be a bit dicier. We have some new rules. But the important thing is 2 of the rules, we have to be very careful about how we apply them. So remember, universal introduction has a restriction on it, and existential elimination is complicated and restricted as well. What are the restrictions? What are the complications? Remember, what we're trying to do with universal introduction is to make sure that the name we're generalizing on is really an arbitrary name. The restriction that accomplishes that is this one. So suppose we're trying to derive a universal generalization from the premise. We're going to try to get everything as F, and the premise that we have is A is F. Here's the business. Take a look at the assumption set for the premise of that inference. So the premise is FA, capital F, lowercase a. That has a name in it, A. That name can't occur in any of the assumptions of FA. So you look at the assumption set for the line that you're generalizing on. And the name that you're generalizing on can't be in the assumptions of that line. That's the restriction. Okay, that's the simpler of the two rules. The name can't appear there. Existential elimination is first a more complicated rule in our system. And second, it has a more complicated set of restrictions. So first, the complications of the rule. When we want to use existential elimination, we have EXFX, for example. We have an existentially quantified formula, and we want to pull off the quantifier. We're not going to be allowed to do that. Here's what we're going to do instead. We're just going to assume that some particular object makes the universally quantified sentence true. It will be an assumption line. So if you have EXFX, you can assume, for purposes of existential elimination, that A is F. I mean, if something is F, then there's some object that will be F. So let's just assume that the object that makes the existentially quantified sentence true is A. So we're going to assume FA. We're then going to derive a formula from FA. And then when we're done with the proof, we're going to discharge the assumption FA by existential elimination, concluding that if that formula followed from A is F, it also follows from something is F. That's the form that existential elimination takes. So we have an existentially quantified formula at some line, call it line G. We assume FA at line I. We derive some formula, phi, it doesn't matter what phi is, that's at line M. And then we get to repeat that very formula on the next line, justifying it by appeal to line G, the existentially quantified formula, line M, what we derived from FA, using the rule existential elimination, discharging line I, our assumed instance. All right, that's the complicated form that this rule takes in this system. It also is subject to restrictions. The name at line I, when you assume an instance, you can't just pick any name you want. The name at line I can't be either in the existentially quantified formula at line G or in the line M that you're going to repeat and justify by this rule, nor can it be in any of the assumptions of line M other than line I itself. Notice what those restrictions do. A is a very special constant. Pretty much, this overgeneralizes, but pretty much nothing that matters involves A in this little subgroup. It could have been B that you used at line I, because it's really only at line I that the constant is going to play a role at all. So here's an example of a case that is going to tempt you to violate the restrictions. Here are two proofs of the same problem. The problem is this. You're given lines 1 and 2, and you're supposed to prove the last line of the proof. Notice, each of these proofs are 7 steps long. One of them is labeled good proof, and the other one's labeled bad proof. So in each case, you are given lines 1 and 2. So you're told At line 1, all f's are g's. For all x, if x is an f, then x is a g. And at line 2, you're told that something is f. And you're asked to derive from that that something is g. It's obvious that that conclusion follows. If all f's are g's and something is an f, then that very thing will also be a g, whatever that thing is. The question is how to go about proving this. So let's look at the bad proof first and see why it's a bad proof. Notice at line 3, we simply remove the quantifier from line 1. We do that by dropping the quantifier and replacing the variable with a constant. In this case, I used a. At line 4, then I did the same thing with respect to line 2. Why did I do that? Well, 2 is an existentially quantified formula, so I want to remove the existential quantifier. I do that by making an assumption. There's nothing wrong with line 4. And there's nothing wrong in principle with the idea of using line 4 by citing the existential elimination rule. So at line 5, that's what I do. I treat line 4 as the derived formula from an initial assumption that I made for purposes of existential elimination. So I repeated line 4 and discharged assumption 4. That fits the form of the rule because 2 is an existentially quantified formula. Notice that's one of the lines I cited. And 4 is a formula derived from 4 itself. So I use 2 and 4 by existential elimination to discharge 4, and then I get FA relying only on premise 2. I then use 5 and 3 to get GA, and then I do existential introduction to finish the proof. But the trick here is I forgot, describing what I was doing, to talk about whether or not I satisfied the restrictions on existential elimination at line 5. So I used the rule properly. It fits the form of the rule just fine. The question is, in addition, does it satisfy the restrictions on the constant that was used? So the restrictions are that the constant can't appear in the existentially quantified formula at line 2. That restriction is satisfied. But it also says the constant can't appear in the derived line that you're going to repeat. That turns out to be line 4, and the constant does appear there. If we can't do the proof this way, what do we do? We'll look at the upper problem. The upper proof does something very similar. We start with the same 2 premises, and at line 3, I switched lines 3 and 4 around, but it doesn't matter. You could go either way. We do FA, and then we do FA arrow GA. FA at line 3 is an assumption. It's an assumption that, again, I'm making for purposes of existential elimination. So if you notice at line 7, I'm going to use existential elimination to finish the proof. The difference is I wait until I get to a quantified sentence before I use that rule. So I have FA and I have FA arrow GA, from which I derive GA by arrow elimination. I then generalize immediately on that formula to get something as G. And remember, there are no restrictions on existential introduction. So at line 6, I get to the conclusion that I was aiming at, but I'm not done, because if you look at the assumption set for line 6, it's bigger than the assumptions that I'm allowed to use. It includes assumption 3, and that wasn't part of the original problem. So what are we supposed to do about that? We have to get rid of assumption 3. So you go back and you look at line 3. What was I doing when I made that assumption? I was thinking A is the instance that makes line 2 true. So the rule I had in mind was existential elimination. That's nice because that's a discharge rule. So if you look at line 7, the justification column, I'm getting rid of assumption 3 by that rule. Which lines did I use? Well, 3 is an instance of 2, so I used line 2. 6 is the line I'm going to repeat, so I used line 6. So the justification column is lines 2 and 6. The rule is existential elimination, and I eliminate assumption 3. That's convenient because look what happened to the assumption set. I dropped 3, and I carry down all of the assumptions that were in line 2 and 6, except for 3. That gives us 1 and 2, and that means we've now got something is G derived just from the assumptions that we were given. The last thing we have to do is check to make sure we didn't violate any restrictions. The restrictions are these. We used lines 2 and 6 to get to 7. And the restriction is that the constant at line 3 can't be in either of those two lines. Notice it's not. There's no constant in either lines 2 or 6. So we made it past the first hurdle. The second hurdle is that the constant can't be in any of the assumptions of the line that we repeated. The line we repeated was line 6. Its assumption set is lines 1 and 3. So the restriction is that the name can't be in any of those assumptions, except, of course, for the assumption that you're discharging, which is line 3. So the assumption line 3 is not relevant here. It's only line 1, and we look at line 1 and say, does the constant A appear in line 1? No, it doesn't. There's no constant in line 1 at all. So this proof satisfies the restrictions. Notice the difference then between these two proofs. The difference between the good proof and the bad proof is a matter of when I apply the The answer is you look first at the conclusion that you're trying to get and what kind of a form it's got. So the conclusion can be any of the following. It can be an atomic formula, it can be a negation, it can be a conjunction, a disjunction, a conditional, or a biconditional. In other words, it can use for its primary form any one of the connectives that we've got. And the strategy you adopt for proving something of that sort depends on the form of the conclusion. The same thing will happen if you adopt a strategy and get stuck again. So long as you can identify what you have to prove in order to finish the proof, you can apply the same proof strategies to that as well. So what are the proof strategies? For atomic formulas and negations, use RAA. It's designed for such formulas. For atomic formulas, simply assume the opposite of that formula, derive a contradiction, and then discharge by RAA and you're done. Same thing for a negation formula. If you don't see how to get a negation formula, assume the unnegated form, get a contradiction, and discharge. For ampersand and double arrow formulas, remember a double arrow formula is really a hidden conjunction. A double arrow is just the conjunction of two arrows running in opposite directions. So P double arrow Q is really P arrow Q and Q arrow P. So we're going to prove both conjunctions and double arrows in the same way, which is prove each of these two parts. So if you're trying to prove P and Q, first prove P, then prove Q, put the two together. If you're trying to prove P double arrow Q, first prove P arrow Q, then prove Q arrow P, and then put the two together and you have your double arrow formula. Now, how you go about proving each of the two parts depends on their form. So if you're trying to prove P and Q, I said prove P. Well, how do I do that? Well, it depends on the form that P has. P can be any of the other forms. It could be an atomic formula, a negation, a conditional, whatever. It can be any of those. So you apply the relevant strategies to whatever form P takes in the conjunction of P and Q. It doesn't matter. With the biconditional, you know what the form of the first conjunct is. If you're going to prove P double arrow Q, you have to prove first P arrow Q. How do you do that? Well, you prove P arrow Q the way you prove any conditional. That's what arrow introduction is built to do for you. So if you're trying to prove a conditional, you assume its antecedent, you derive its consequent, and then you discharge by arrow introduction, summarizing that little subproof. The last one that we haven't talked about is how do you prove wedge formulas? Well, if you have a wedge formula, you assume its opposite, and then what you're going to do is apply a derived rule immediately. The derived rule in question is called De Morgan's rule. So I'm going to talk about some of these derived rules, but the reason for using this derived rule is because it generates so much information. So you're told that P or Q is false. That's what you're trying to prove. So you have tilde parentheses P wedge Q, close parentheses. When you apply De Morgan's rule to the negation of a disjunction, you end up with a conjunction. You end up with not P and not Q. So think about what a disjunction says. P wedge Q says, well, one of the two is true. Either P is true or Q is true. If you have that claim is false, what does it take for that to be false? Well, they both have to be false. So P has to be false and Q has to be false. So De Morgan's rule tells you if you have the negation of a disjunction, you can conclude that the first disjunct is false and the second one is false, not P and not Q. Similarly, if you have the negation of a conjunction, that tells you that one of the two is false. So if you have the negation of P and Q, you end up with not P or not Q. So what we're talking about here is the more useful of the two De Morgan's rules, because if you have the negation of a disjunction and you apply De Morgan's rule, you get a whole bunch of information. You get a conjunction, which allows you to simplify immediately to the first conjunct and also to the second one, whichever one you want. Maybe you want both. So if you have a disjunction that you're trying to prove and you don't see how to prove it, assume the opposite and immediately apply De Morgan's rules. Technically, we would have to prove De Morgan's rules before we're allowed to use them. I'm not going to take the time to do this. You did this in the first baby logic course. So all I'm going to do is assume that we've proven them. You can do the proof if you want on your own. But among the derived rules, De Morgan's rules are among the most important. The most important derived rules are ones that have negations out front. The reason for that is because if you have a formula governed by a negation, there simply are very few primitive rules that let you use that premise for anything. Wedge elimination lets you use it, but in general, you're paralyzed. Remember, no proofs can appeal to subparts of a line. All of our rules, all of our proof rules and derived rules require applying the rules to entire lines. So if you have the negation of P or Q and S, put the parentheses however you want, you can't use any part of the P and Q or S. You can't use any part of that because it's governed by this negation sitting up front, and you can only apply rules to the entire line. So among the most important derived rules are rules that let you run a negation through some other connective. So you've got a negation governing a wedge. You've got a negation governing an ampersand. De Morgan's rules tell you how to drive the negation across that connective and end up with a new formula that isn't primarily a negation formula. If you started out with a negation of P or Q, you end up with a conjunction. It's got negations in there, but its primary form is an ampersand formula. Same thing for ampersand. If you have the negation of an ampersand formula, you end up with a wedge formula. It started out as a negation of something, and it ended up as a wedge. Those are the two forms of De Morgan's rules. We also have rules for negations sitting out front of arrows and double arrows. We will call those neg arrow and neg double arrow. So neg arrow works this way. What does it take for a conditional to be false? Suppose your conditional is P arrow Q. There's exactly one way for a conditional to be false: true antecedent, false consequent. So if you run a tilde across an arrow, you end up with a conjunction. The negation of P arrow Q is P and not Q. The negation of P double arrow Q is just a double arrow formula, where the negation is attached to one of the two sides. You get to pick which one you want. So if you've got the negation of P double arrow Q, you end up with not P double arrow Q or P double arrow not Q. That's because P double arrow Q just tells us that P and Q have the same truth value. By putting the negation on one of the two, doesn't matter which one, you then say, no, they've got opposite truth values. That's what it is for the double arrow formula to be false. So among the most important derived rules are rules concerning negation. That's fundamental to propositional logic. The fundamental derived rules for predicate logic are quantifier exchange rules. And there are four forms of these. These are called dual rules. That's an important concept because it keeps coming up when we get to modal logic. Dual rules are rules that tell you that in some way or another, two of the operators or quantifiers in the system are interchangeable in some way. So in our case, in predicate logic, we've got a universal and an existential quantifier. They are duals of each other. The way the dual rule works is you take either one of the two quantifiers standing alone. Start with the universal quantifier. If you've got the universal quantifier, you can replace it with the existential quantifier preceded and succeeded by negations. So for all x is logically equivalent to not exists in x not. Suppose then that everything is red. That's equivalent to it's not the case that there's something that's not red. The dual rule you should hear involves two negations, one before the quantifier and one afterward. So if you started with the existential quantifier, some people have brown hair. It's false that everything has non-brown hair. So there exists an x, fx, is equivalent to not for all x, not fx. The other two forms of the rule simply arise when you already have a negation in one place and you want to move it. So suppose you have for all x not fx. That will be not, there exists an x, not fx. But the double negation drops out. So if you have for all x not, you can just replace it with not some. And if you have some or not, something is not f, you can just say not for all x, fx. Not everything is f. So among the most important rules are first, the negation rules. How do you drive negations across connectives? And quantifier exchange rules. There are also other useful derived rules, and you can use any of these that you want in any proof that you're talking about. I will simply put up a table showing what these rules are. You can use them at any point in a proof and cite the relevant rule. So that's a summary of the syntax for the system we're going to be using.